Welcome to Chapter 8, Encapsulation into Classes. So we've just begun a new part of the course and opened up notebook number 8. So in this chapter, we're going to encapsulate all of our work from the smoothing and model building chapters into Python classes. So what does encapsulation mean? It means bringing together data and functions that act together to complete similar tasks. So in the previous chapters, we have all these functions, and what we're going to do with these functions is place them under this CasesModel class. So it encapsulates all of that work into a single class. All right, so below, we will go over what the CasesModel class is, and we'll see that it is responsible for performing nearly all the tasks after downloading the data. So we already have the prepare data class with the run method to go get and download the data and do a little bit of cleaning. The CasesModel class will smooth, train, predict, and then do some work to combine the results. So as you'll see, many of the methods below are actually written as previously as functions. So they'll be essentially the exact same code. So a lot of data will come out of the CasesModel class. And what will happen is for every single area that we have, we'll have the smooth data, we'll have the lower and upper bounds, we'll have the initial parameter guess, the fitted parameters, the daily predicted cases, the cumulative predictive cases, and then we're going to do a little bit more work to combine the actual and predicted values into a single data frame. Okay, so let's go ahead and look at this CasesModel class. So after we do our imports, we're going to define some constants over here. So this is the same constants we use for prepare data. So we have two different groups, world or USA. There's two different kinds of data, cases or deaths. We're going to define a minimum number of observations that we will just not make a prediction unless we have at least this number. Okay, so our cases model, as you see, can take any model. So what we've done here is we've placed our general logistic function outside of the CasesModel class because we can pass in any model that we want over here. And this is just to help out with the general logistic, or with SciPy's least squares. This will calculate the error. Those go outside the CasesModel class. So let's go ahead and look at the CasesModel class. And it's going to look somewhat similar to the predict all function that we've been using. And it is pretty similar to that, which does encapsulate many of the functions. But this CasesModel goes ahead and does a little bit more. So you'll see the difference in a bit. Let's go through the arguments that are passed to it when we first initialize it. So you're going to give it the model. So this is going to be could be any model, but for our purposes, it will be the general logistic function. And I have the documentation over here, so we'll go through like that. The data is the dictionary that results from this prepare data.run. So it has 4 different keys: world cases, world deaths, USA cases, and USA deaths. So that's going to be the raw data that we'll use to smooth, train, and then predict. The last date is the last date to use for training. This can actually be none, so we could actually just predict into the future without being able to test our results. End train. So this is a little bit of a new variable. So this will be the number of preceding days to use for training. So what is the number of training days we want to use? And it's new because whenever we decided to model new waves just based on previous n days, so this is what will be used. We'll say, all right, if this is 50, we'll just look at the last 50 days. If it's 100, we'll look at the last 100 days. It doesn't matter how many days of data we have. We're going to set a number here to train on. And smooth, we've seen this before. It's just the number of points to use for low s. And predict, we've also seen, is the number of predictions to make. ln min and ln max, these are new, but these are just new parameter names. We covered them in a previous section when we wanted to estimate the lower and upper bounds for our parameter L. So this is the number of days to extrapolate the very last percentage change into the future to see where the upper bound could be or where the lower bound could be. And then any keyword arguments that are forwarded to SciPy's least squares function. Okay, so here in our init method, we're going to set all these arguments that have been passed in and set them as attributes. The only thing that we do a little bit of work for is getting the last date. So you can set this as none. And so we're going to call, we have a little method over here that will just use some logic to, if it is none, we're just going to use the very last date of data that we have. Otherwise, we'll just use that date itself. A couple other items here. So we're going to just prepare ourselves for our prediction. We're going to get the first prediction date, which is just a single day after the last date. And then we're going to create a pandas date range to get ready for the index of our data frame that will result after a prediction. So this will just be from the first prediction date through the n number of periods. So we're just preparing to the index ahead of time. All right, so to store all of our results, we're going to create a dictionary for for all of the results, as you can see here. So we're going to save the smooth data over here. So it's going to actually be a dictionary of dictionaries. So for the world cases, we'll have a dictionary mapping each area to its smooth data. So like Italy will have its own series in here, United Kingdom, in USA cases, Texas, New York, Florida, whatever. They'll each have their own series over here. So all of these results will be stored like that. So for the bounds, the initial guess, the fitted parameters, the daily predicted values, the cumulative prediction, we're going to store all of this as a dictionary of dictionaries, where the inner dictionary is the area mapped to its series. We're also going to, these dictionaries will be used below. So we're going to combine the original and then the predicted into a single data frame. Okay, so now we're going to see some functions which are now methods that we've already defined previously. So here's the smoothing. So this is basically the exact same code as before. It is now just converted to a method. This method is actually new. It's just a single line, but this is used to capture the most recent waves. So before we were using all of our data for the training. This will just select the last n train number of observations. So that's all this is doing. So whatever we set that n train to be. The next two we saw during the automating setting of the bound. So we're going to automate the process of finding the L lower and upper bounds. And then we're going to use that method in here to get the bounds for all the parameters plus the initial guess. So we've already seen that. This method was defined a while ago to train the model using the least squares function from SciPy. We're going to then, this method we've already seen before as well. So we're going to get the daily predicted values. From that, we're going to get the cumulative predicted values. We have a couple of methods here to do some data combining. I will cover those in a little bit. And then we come down to our run method. So this is our method that's going to call the other methods to do all of the work. All right, so this is sort of like that predict all function from above, but it's going to be done on each and every area. So we begin by instantiating all those, or initializing all those dictionaries to contain the data. Then we're going to go through each one of the groups. So we have those two groups, USA and world. We're going to use this to create the key of the dictionary, so either USA cases or world cases. Then we're going to get that data frame, so just the USA cases or world cases as a data frame. So that's going to be stored as DF cases. And now we're going to go through every single area. So this is what this inner for loop does. And the way it does that is by calling the items method of a data frame, which returns every column as a series and its column name. So that's what area and S are. So you can think of a data frame as a dictionary where the keys are the column names and the values are the values of each column. So here we have the column name, and then the column values are a series. So for every single area in those cases, we will smooth the data using our smooth method. We'll get the training data. So that's just the last n that we choose to do. So we're not going to use all of the data that we have. We're just going to use the last 50 or last 100 or whatever we choose to do. In the case that we don't have the last 50. We're just going to say the actual n train. Say we only have 40 observations, but we set our n train during init as 50. We don't want to use a different number, so that's what this does. So we get what is the actual number of training observations? Okay, so now we have a if-else statement here, and what this does is if we do not have at least 15 observations, we're not going to do any training. So we'll just set the bounds. We'll just make the missing values. The initial guess will be missing. We're not even going to use that. The parameters, this is the fitted parameters. We're just going to make them missing. We're not even going to try. We're not going to make an attempt over here to make a prediction. We're just going to say the daily predictions are 0. You could use some logic over here to make them a little bit better, but there aren't too many that have less than 15. So this is just like an edge case, not super important. Now for everything else, this is going to be almost all of our data, all of our areas, we're going to get the bounds and our initial guess. Then we're going to train the model. So for every area, we're going to train the model. We're going to get the fitted parameters. We're going to use those fitted parameters to get the daily predicted values. Now we're going to hop out of this if-else statement. So we have all of these. We have the bounds, the initial guess, the parameters, and the daily predicted values. We're going to get the cumulative predicted values using this get predict cumulative method that we covered above. Okay, so that's the bulk of the work right there. Now the rest is going to be just saving this to data frames. So what we'll do here is, these are all those initial dictionaries that we created. So for each area, and GK is just this, remember, this string of either USA cases or world cases. So this is the dictionary of dictionaries. Each one of these, smooth, bounds, p-naught, params, predict daily, predict cumulative, these are all dictionaries of dictionaries. Okay, so for each, we're going to add a new entry into the dictionary such that each area is mapped to its new value. So here, for the smooth values, we're going to just give it what we found for smooth up here. For the bounds, this is the only one. These are always series, by the way. For the bounds, this is one where it's actually going to be a dictionary of data frames because there's lower and upper bounds. So that's the only one that is going to be different. The initial guess, this will be a series area mapped to a series. For us, it will be 5 values because there's 5 parameters. This is the fitted parameters. Again, the same thing. So the series name, the area name, mapped to a series of 5. The predicted daily, so a series mapped to the daily predictions, and we just turn them into integers. And same thing for the cumulative. So we're just saving our results right here. That's all we're doing at this point. Now, after we've done all of this work for every single area, so we have all of our data, what we're going to do is we're going to convert everything into a data frame. So instead of just having a bunch of areas, a dictionary of areas mapped to series, we're going to combine them into data frames. So let's go back up here and say convert to DF. So we're no longer going to have a dictionary of dictionaries. We're just going to have a dictionary where it is mapped to a data frame. So we're going to take all of those areas. So over here, and you can place this right in the data frame constructor, and that's what the data frame constructor does. Is if you have a dictionary of strings mapped to series, well, it's just going to make a data frame directly from that. The only different one over here is this bounds. So we have a mapping of areas to data frames, so we have to use the concat method. We can't just use the data frame constructor, and so we're just going to concatenate them all together like that. We just do some rounding over here after that, and then we're going to do the same thing right here. So we're going to create a data frame using the constructor for the initial values, do some rounding again. Same thing for the fitted parameters, the daily predictions, and the cumulative predictions. So these will all be data frames where the data frame column names are the areas and the values are just the values for that particular, about whatever it is. All right, then we have one more method, and we're going to combine the actual data with the predictions, and this will be useful when we're modeling deaths down below. So that's why we're doing this. So it'll just we'll just go through each one of the cumulative each one of the cumulative data frames over here, and we're going to get the actual from our raw unprocessed data, and we're just going to concatenate them, concatenate the actual with the prediction. So it'll be one long string of data from actual through prediction. So we'll have it all together. You won't know just by looking at this data frame where the predictions start and or where the actual date ends. So that's all we're doing here. We're going to create this single data frame that has actual and predictions for both the cumulative and the daily, and for the cumulative smooth and the daily smoothed. So that's that last bit over there. And then we have one more method, which we've already seen before, which just plots the prediction along with the actual. Okay, so that's it for covering what this cases model does. So it's a whole lot. I know it's a lot to digest in a single video, but we've covered most of the pieces throughout the course, and now we're just kind of combining it together, and the fancy word for that is just encapsulation.